Well, welcome. Whether you are here for the 50th or the first time, I'm super excited to see y'all here. Thank you, Jeff and Irene, for joining us on the camera. Makes me feel like I'm not just yelling into the void, but actually here with real live humans. Love it. On that note, y'all, if you can turn your camera on this evening, please do. This is a participatory workshop. And if you feel nervous about participating, that is good because we are here to learn tonight. So lean into any nervousness or discomfort you have in terms of answering questions or participating. This evening you'll have some chances to do that, and this is a pretty good place to practice speaking up in technical ways. So here we go. What is a recursion? Who would like to give a try at attempting to define recursion? Raise your virtual hand with the reactions button if you'd like to give an attempt here. Guesses are welcome. Yes, Michael.
So kind of how I understand recursion, it is when a function invokes or calls itself within the function. So it's kind of like a weird kind of like repetitive mechanism.
Indeed, you hit on a lot of good things there. When a function calls itself. When a function calls itself. And recursion is a fundamental concept in computer science. And it is indeed when a function calls itself. And that could look a variety of ways. We'll look at a couple examples today, but the examples that we look at today are by no means exhaustive. There's lots of different ways to apply this. But at its core, this is recursion. It's when a function calls or invokes itself. And what this gives to us is, although it might not feel this way at first, I'll preface that with that, but eventually, once we understand this concept of recursion and how it's applied, it enables us to write more intuitive and maintainable code and more declarative code as opposed to imperative code, where we work towards our base case, towards a solution, towards the smallest instance of the problem. And we'll look at that. We'll look at that today. And something also that Michael said was, he mentioned repetition, right? So we're going to talk about repetition through iteration in a few minutes. But ultimately, if you think about a function invoking itself, inherently there's some repetition happening there, right? Like every time a function invokes itself, it is doing some sort of repetition. So we'll talk about that a little bit more in a few minutes. But first, yes, the roadmap. We are going to talk about repetition through iteration. We are going to talk about what is recursion. We'll even talk about multiple recursion, and I'll have a fun challenge to leave y'all with on that. But before we do any of that, we're going to just build out our shared understanding, some shared vocabulary to help us dive into this sometimes confusing concept of recursion. And so before we even get there, we're going to do some quick diagramming and some quick review of these 4 principles. Okay, so we are going to be exploring this tonight, exploring this concept through diagramming. So before we get into recursion, where a function is calling itself, we're going to diagram out a function that is not recursive. We're also going to diagram out some repetitive functionality that is not recursive before we get to the recursive case. Let's start here, my highlighter back on, and we'll talk about these 4 things. So the thread of execution, right? This is a fundamental need to know about JavaScript. JavaScript is what we call single-threaded, and it's synchronous. And so this means that JavaScript can only ever do one thing at a time. And the way that it's going to parse code, that it's going to evaluate code, is from the top of the file and it's going to move its way down the file, just like we read in English and some other languages as well, reading the code, executing code from top to bottom, from left to right. And this is going to be important when we talk about different types of recursion as well. But single-threaded. So this is our first principle. As our code is interpreted by JavaScript, we also need a place to store some information. And that is where memory comes in. JavaScript's memory is a lot more programmatic than our own. So there is a very specific place for JavaScript to store data and labels that we can use to then access that data. And that place is called memory. When we are working in the global execution context, that is called global memory. And when we are working in a local execution context or a function level execution context, that it will be referred to as local memory or function level memory. If you're not familiar yet with functions, you should also go to the Intro to JavaScript Functions and Objects workshop. It's a fantastic way to build out your understanding of what functions are and why we have them. But we can think of functions as sets of instructions that we want to repeat again and again. They're going to allow us to bundle up some code to use later through an invocation. This is going to help us keep our code dry. Virtual hands, what does dry stand for? What do I say? What do I mean when I say keep our code dry? Yeah, Queen.
Don't repeat yourself.
Indeed. What does it stand for?
Don't repeat yourself.
Don't repeat yourself. Love it. Yes, don't repeat yourself. And we'll see some instances. Don't repeat yourself of how recursion solves this problem. Okay. And then the call stack. We're going to include this in our diagramming today as well. The call stack is going to allow us to keep track of where we are in the code, where our thread of execution is. Whichever stack frame is on the top of the call stack is going to be where our thread is currently working, currently interpreting, executing code. All right, so with all this in mind, we're gonna go through a little diagram here. Okay, so we have this function, or we have this code in general, right? And again, JavaScript is going to evaluate this code from top to bottom, left to right. And there's some intricacies about this that we will explore as we go through this diagram. So we are going to read this code as if we were JavaScript, interpreting and executing this code. So we have the global execution context, which is just going to be this whole area. We also have global memory, and we have the call stack. And we are going to, we know that we are in the global execution context. So that's what's going to sit on the bottom of the call stack. Oh, lost my voice a little. And that means that that's also where our thread of execution is. It's in the global execution context, because that's on top of the call stack at this moment. So we are going to start with Nina. Nina, using your best technical communication, please walk us through this code on the left as if you were JavaScript interpreting, executing this code.
All right, so we are going to declare a new function labeled multiply by 2 and store it in the global memory as a function definition.
Awesome.
So next line, we are declaring a constant output.
And where are we declaring that?
In the global memory.
And Nina, you've done everything right. Tell us why did you skip these lines?
Because this function has not been invoked yet, so we are not going inside of it.
Awesome, awesome. Okay, continue.
So the output is undefined at this moment. It's gonna be, so its value will be the evaluated result of invoking multiply by 2 with argument 4.
Indeed. And how do you know that this function definition is being invoked?
Parentheses.
Yes, y'all, the parentheses tell us that this is a function invocation. And you also mentioned that it has an argument 4. What is, so this is an argument. What is this? What is n?
This is a parameter.
Indeed. So a parameter, y'all, in our function definitions are placeholders for eventual arguments. Okay, all of this is great. Nina, what happens when we invoke a function definition?
So we are going to push multiply by 2 stack frame onto the call stack and open a new execution context.
Indeed, and I'm just gonna abbreviate this, y'all. We are pushing this stack frame onto the call stack. We are opening a related local execution context here. What is the first thing that we want to do, Nina?
So we want to pair our argument with the parameter.
And remind me, what is the parameter in this case?
N.
And where will we put this?
In the local memory. N
Okay.
will be assigned to 4.
All right. And then what happens?
We are going to return n times 2, and n is 4, so we are going to return 8 to the global memory under label output.
And why are we returning it here to output?
Why we are returning it? So we are returning it to the execution context where it was invoked from.
You're very close. You're very close. We're returning it specifically to the site where it was invoked. So not just the execution context. We're not just to global, but very specifically to where it was invoked in that execution context. So associated with the label output. What else do we do here?
So now we are going to pop off the stack frame from the call stack, and the local execution context gets garbage collected.
Indeed, we're done with that execution context. Amazing technical communication. Nina, great job, y'all. Don't worry, if you are hoping that you would get to practice your technical communication, there will be lots more opportunities tonight. How are we feeling about this diagramming practice, looking at the global execution context, the global memory, and these function level execution contexts? Thumbs, can I get some thumbs on this? Cool, cool, cool. All right, let's talk about repetition. That was the first bullet, so to speak, on our roadmap. So repeating tasks, super common in JavaScript, right? So they're so common. It's so common to loop over things, loop over lists of data, that we have keywords for this. Who has written a for loop before? A few of us. Who has written a while loop before? Yeah. These are specifically for this repetition so that we can iterate over a list and do some repetitive behavior. So when we have this type of repetition, when we're using either a while loop or a for loop or one of these pieces, there are really 3 things that we need. We need an initial value. We also need a breaking condition, and we need an update expression. So let's talk about each of these, right? So the initial value is going to be someplace where we're beginning. In this case, I'm going to give you 15 seconds to look at the code, and then I'm going to call on a few of you to ask what is the initial value in this code, what is the breaking condition, and what is the update expression. So take 15 seconds, take a look at the code, and then I'll I'll choose some folks. Let's do it. Ryan from CA, what is the initial value?
3.
Okay, yes. The initial value when we invoke some naturals is going to be 3. What is the initial value in the function definition itself? What will we be pairing 3 with?
With n, the parameter n.
Indeed. N is going to be our initial value here. Okay, thank you, Ryan. Let's go over to Michelle. Michelle, what is the breaking condition?
When n equals 0.
Close. I mean, yes, this is true. This is true. To think about it programmatically, we're looking at this parentheses here, right? So not only when n is equal to 0, but really when n is no longer greater than or equal to 1. Whether it's 0 or -1 or something else.
Yep.
Actually, we'll never get to -1, but we'll leave that there.
Okay.
Awesome. Thank you, Michelle. Let's go on over to Irene. Irene, what is the update expression?
I think it's n equals n minus 1.
Indeed, yes. N equals n minus 1. This is how we are moving towards our breaking condition. Y'all, what would happen if the breaking condition was never met? Yeah, Roger.
We would create an infinite loop.
Yes, yeah, infinite loops. Who has unintentionally created infinite loops at some point? Aha, yes, me too. This is something we want to avoid, right? Our computers are not infinitely able to process our requests like this, so we do need a breaking condition. Okay, let's diagram this out. These 3 things in mind, I've written them here so that we have them, so that we can easily reference them. Initial value, breaking condition, update expression, and I'm just going to write down what we said that they were. The initial value is n. The breaking condition, when n no longer equals or is no longer greater than or equal to 1. In other words, as Michelle said, when n is 0. And the update expression, n equals n minus 1. We're reassigning the value of n to be 1 less than it was before. Okay, we are going to go on over to, who haven't I heard from yet? Connor. Connor, can you walk us through this code as JavaScript would, as it would interpret it?
Yeah, sure. So we are going to declare our function SumNaturals with the parameter n.
And where are we going to declare this?
In our global memory.
Awesome.
Then we're gonna. Oh, sorry.
And just to clarify, JavaScript cares not yet about the parameter, just cares that it's a function definition. So it's going to store this function definition in global memory. What's it going to do next?
We're gonna skip the guts of our function, and then we're going to, so curly brace, open curly brace, close curly brace, and then we're going to declare the constant with the label output equal to the evaluation of the function SumNaturals with the argument of 3.
And where are we going to declare this?
Global memory.
Awesome job. Yes, and this is going to be equal to the evaluated result or the invocation of SumNaturals passing in the argument 3. Right now, we JavaScript do not know what it is. What do we need to do? Oops, I forgot. Global's down here. We're going to pretend it was there all the time. It always is. All right. What do we need to do when a function is invoked, Connor?
Push it onto our call stack.
Indeed. Indeed. Okay. And what else?
Then we're going to create a local execution context for that function.
And what's the first thing
And
we're going to do in that local execution context?
we are going to declare a variable with the label of result and set that equal to 0.
Ooh, before we even do that, before we even get into the code block, what do we need to do first?
Pass it in the argument.
Yes. We're going to pair our parameter, which is n, with our argument, which is 3. Okay, continue.
Then we are going to declare our variable with a label of result equal to 0.
All right. And now we have hit, sorry to interrupt you. We have hit our while loop. We are going to start a looping. So I'm going to just set up some things in our execution context so that we can move through this in a timely manner. So what happens first with our condition? We are here.
Yeah. Honestly, I don't know the order, but I'll take a guess. I mean, that while we haven't met our breaking condition, so while n is yet greater than or equal to 1,
And what is n in this scenario?
it has been passed in as 3,
And is 3 greater than or equal to 1?
as far as I know.
Me too. If it is not, I think we're in an upside down world and we should all run for the hills. But it is, as far as we know, 3 is still greater than or equal to 1. So what happens here, Connor?
Then we are going to set our variable result equal to the value of result plus n, which right now is 3.
Indeed.
So
And
result
what
is
is result?
Yeah, so result is going to equal what's assigned to result right now, which is 0, plus what's assigned to n right now, which is 3. So the evaluated, well, result is equal to 3.
Awesome. And then what happens?
We are going to decrement the value of n by 1. So n, which is 3, is going to be 3 minus 1.
All right. I was moving my return down and I lost you for a moment. Let me just move this stuff down. We have our update expression, which is indeed the decrementing of n. N is 3 minus 1, and so n will be 2. Okay, fantastic. Fantastic. What happens next?
If we were to, we have to go back through our while loop, because
Yeah.
if we were to, sorry, what'd you say?
Yeah, absolutely. So but before we know if we're going back through our while loop, what do we have to check first?
Yeah, our what'd you call it? Breaking condition.
Yes.
So to see if the value of n is still greater than or equal to 1. It is, yeah, and 2 is still greater than or equal to 1.
2 is still greater than or equal to 1. Hooray, we are still living in a somewhat logical world. So what do we do in this case?
Yep. We will run through the contents of our while loop again. So result, which I think we set previously equal to 0, which was result, which we initialized within the function, and then plus n, which we passed in as 3. So then result became 3. So now we're through our second go round of the while loop. So result is now going to equal the current value of result, which is 3, plus n, which is 2.
And what is 3 plus 2?
5, I hope.
I hope so as well. Awesome job, Connor. Awesome job. All right. We have gone through the while loop again. What do we need to do now?
I think you called it your update expression. So let's decrement n again.
Indeed. And what is n currently?
N is currently 2, and we're going to set the new value of n equal to n, which is 2 minus 1. So that equals 1.
Awesome job. Almost there. What happens next?
We need to check our breaking condition. So if n, which is currently 1, is greater than or equal to 1, we will go through the while loop again. And 1 is greater than or equal to 1.
Shocking. Okay. What happens to result?
Yep. So result is now, what is result right now? We're up to 5. So result is 5. And so we're going to add the current value of n to the current value of result. And n is currently 1 and result is currently 5. So the new value of result is going to be 6. And
Okay.
then we will do our update expression one more time. And we're going to set n equal to the current value of n, which is 1 minus 1. So that will set the value of n to 0.
All right. And then what do we need to do?
Check our breaking condition and see if 0 is greater than or equal to 1, which it is not.
How exciting. It is not. So where do we go from here?
We can break out of our while loop and return our result.
And where are we returning our result to?
We are returning, where are we returning our result to? I know that it'll be like the evaluated function of some naturals, which is result will get passed into the constant that we labeled output in global memory, but I don't know, yeah.
Yeah, that's exactly right. So it is going, when a function definition returns, it's going to return to wherever it was invoked. So since we're pairing the evaluated result of sum naturals 3 with output, it will be stored in output. Awesome job, Connor. Great technical communication. Fantastic work, y'all. How are we feeling about this so far? A couple more steps in this diagram, but all good. Cool, cool. All right. Once we return out of a function, it is popped off of the call stack, and the execution context is marked as eligible for garbage collection. All right. Yes, Roger.
Would you go back to the previous slide?
Yes.
Yes, thank you. So the last line, why we have a 0? Shouldn't be just 3 to 1 and to 6? Because I tried to diagram this myself, I couldn't get to 0.
Yeah, this is a great question. Y'all, the reason why there's a 0 here in this diagram is because there is some disagreement around mathematicians around whether or not 0 is a natural number. And that is what this function is intending to do, is sum all natural numbers. So whether or not we include 0 in that sum, 0 is 0. It's never going to be, it's never going to change the end result. But we've included 0 in this comment. You do not need to include it in your summing of natural numbers. But I'm glad that you asked that question. Yeah, you would be surprised. I don't know if there are any mathematicians in the room. I'm not raising my hand because I am one. I am not. But I have heard folks have strong opinions about whether or not 0 is a natural number. Good question, Roger.
Thank you.
Okay, we were able to accomplish this repetitive task, right? Summing all of the natural numbers between whatever number that we passed in, whether it's 3 or 10 or 9, this while loop is going to succeed at summing all of the numbers between whatever we pass in, including whatever we pass in, and all the way down to 0. These are all our natural numbers. Let's just talk through the pros and cons of this method. It works, right? It's a functional way, a logical way to do this. And we can reason about it as well, right? This slide always cracks me up. It gets the job done, but it could be cleaner. Yes, this is true. And right now, this solution is pretty intuitive for folks who are familiar with the imperative paradigm of using for loops or while loops, right? But thinking through each step is a little bit exhausting. We're going through our breaking condition, we're going through our update expression, we are looking at our initial value, right? And there must be a way to do this without having this verbose code. The reason why we're talking about this now is because it is going to help us understand what we're trying to do with recursion. And recursion is going to be a way to do this in a more declarative way. That is, it's going to allow us to express what we want to be returned, the smallest instance of the problem, instead of going through it very iteratively. I'm just talking a lot. So let's start to get into it and look at some code. So again, recursion. I don't know if anyone has Googled recursion. Has anyone Googled recursion? Just the word recursion. There's a nice little Easter egg joke in there from the Googlers about recursion. Yes, to understand recursion, you must first understand recursion. If you don't get this joke yet, no worries, but one day you're gonna laugh at this. A recursive function, and we said this earlier, a recursive function is one that calls itself, and more specifically, it's one that solves a repetitive problem by calling itself. And each function invocation is going to break the problem down to smaller and smaller pieces, right? So that it can get to the smallest possible solution in order to generate the result. Who knows, has a guess as to what the smallest possible solution is when we're talking about recursion? There's a term for this. Raise your virtual hand. You know the term. Yeah, Connor.
The base case.
Indeed. Indeed. The base case. I didn't realize that my pen and my highlighter are purple today. Clearly I'm having a purpley day. All right, so base case. And if we think back to our repetition, let's just go back here for a moment. We had an initial value, a breaking condition, and an update expression. Connor, what do you think the base case is most similar to in this scenario?
The breaking condition.
The breaking condition. Yes. And what about, well, we'll look at some code before we look at the update expression. But a base case we can think of a little bit like a breaking condition. All right, so we are going to take this one step further. Before we look at the code, I just want to point out this pattern of the sum naturals problem, right? So the sum naturals problem basically said that we could take some number n and we could sum all the natural numbers between n and 0 by adding n plus n minus 1 plus n minus 2 plus n minus 3 until we get all the way to 0, right? Until n minus whatever this is 0. And so we can use recursion to write this out programmatically. Let's look at it. Before we look at it, let's further explore this base case and other terminology. So we said with repetitive code, right? With our iterative approach, we have a base case. We have, we have a breaking condition. We have an initial value and we have our update expression. In this case, we have our base case, the simplest version of the problem that can be answered directly. We also have a recursive case, and this is going to be the smaller and smaller versions of the problem that we're trying to solve. What does this kind of map to in our repetitive example, in our iterative example? If the base case was the, where am I going to write this? If the base case was the breaking condition, What is the recursive case? Any guesses?
Update expression.
Yes. This is what is moving us closer and closer to our breaking condition in our iterative approach, or to our base case in our recursive approach. And what about initial value? Which one could that map to? Just kidding, it's the same. They both have initial values, right? So you can think of a base case as the easiest thing, that the smallest, simplest part of the problem. And let's just use an analogy. I love some analogies here. This is probably an analogy that you've heard before. Let's say you're online somewhere. Is anyone going to any concerts or festivals soon? The weather's getting nicer in New York, so I'm looking forward to standing in a long line so that I can go get some good food or some good drinks at an outdoor show. Anyway, I digress. If you are in a line and it is winding around the corner because it's summer in New York or wherever you are, and you want to know how many people in front of you are in line, you could tap on the person in front of you. You don't want to leave the line, right? If you leave the line, you're going to lose your spot, and that's no good. So you tap on the person in front of you and say, hey, how many people are in front of you? And that person's going to be like, I don't know, I'm like as far back as you are, but let me tap on the person in front of me and find out how many people are in front of them. This is going to be the repetitive functionality, right? The function will be, if there's someone in front of us, tap on their shoulder, ask how many people are in front. They, in turn, will say, I don't know, because there's still people in front of them. As long as there's someone in front of another person, and this is also assuming that we can't look around the corner and make a guess or count. As long as there's someone in front of another person, then we have more invocations of that functionality to run, more shoulders to tap on. Once someone taps on someone who is at the front of the line and there is nobody in front of them, we have reached the base case, right? That person can turn around and say, yeah, there's no one in front of me. It's just me. And so then the person behind them says, okay, so there's just one person, and then there's me, so that's two. And they turn to the person behind them and say, okay, there's two. And that person's all right, if there's two of them, there's one of me, that means there's three. And we'll bubble back up all the way up the line until we get to me waiting to hear how long it's going to be until, let's be real, until we use the restroom. There's all sorts of lines at festivals, but the one where you really want to know how long it's going to take is when you're waiting for the restroom. So the base case in that case is when the person being asked how many people are in front of them are at the very front of the line. And the recursive case is anytime anyone else is tapping on someone's shoulder. If there's a shoulder to tap on, we are recursing through this functionality of tapping on shoulders. If there's no shoulder to tap on, we are at the base case. We start returning the result back up. But let's go back to our sum naturals example and get started with this. Okay, so I would love a volunteer. Who would like to walk through this code? Maybe somebody I haven't heard from yet. Anyone want to give it a go? Nathan, love it. Okay, Nathan. Walk us through this code as if you were JavaScript.
I'm going to try my best. Okay.
You're going to do great.
Oh, thank you. So we are declaring a function, sum naturals, and we are saving that to the global memory as a function.
As a function definition. Awesome. Yes.
Function definition. Yes, that's right. And then everything that is within that function, we don't care about because JavaScript is just like, okay, I see that that's a function. I don't care about anything else.
All wrapped up in here.
Yes.
Yep, go on.
And then we're going to jump down to the very bottom and declare a constant that has the label output.
And where are we declaring this constant?
It's going to be declared in the global memory.
Okay, and what is the value of output going to be?
So for now, it's going to be undefined until we figure out what is the evaluated result of some naturals with the argument 3.
Awesome. So we are, what does this mean in particular? What do we need to do when we see some naturals invoked with the value of 3?
So JavaScript is going to see the parentheses and be like, oh, so you're calling that function. So I'm going to pop some naturals onto the call stack.
Quick distinction. We pop stack frames off the call stack.
I'm sorry, push.
Awesome. Great job.
I'm nervous right now. I'm not thinking straight.
You're doing great. Okay, some nats is on the call stack. What else do I need to do?
And so we're going to open up a local execution context.
Look at this. Here it is. I'll put it up here.
And for the local memory, we're going to assign the parameter n to the argument 3.
Awesome technical communication there. N equals 3. And I've added something additional to our diagram, and this is going to be important when we're thinking about recursion, particularly as we open more and more stack frames. What is the call site? What was the execution context in which sumnats3 was invoked, Nathan?
It was within the global memory?
It was within the global execution context. Yes.
Yes.
Cool. All right, we're going to start keeping track of this call site, and we'll start to see why as we go through this problem. Okay, keep on going. You're doing great.
Thank you. Trying my best. So the first thing that we're going to go into is that we see a conditional statement that says if n is less than or equal to 0, which n is equal to 3 right now.
So is 3 less than or equal to 0?
It is not.
It is not. So what happens next?
So we're going to skip that and go down to the else statement. And we're going to return n, which is 3, plus the evaluated result of some naturals, where n is -1.
And what will that evaluate to? And what is n minus 1?
So that's going to open up another local execution context.
You are right, it is. But what, and I could do this math, of course, but just for the sake of you walking through the problem, what is n minus 1 in this? What should I put in the parentheses?
So, so for the parameter n minus 1, our argument that's going to be passed into that is going to be 3 minus 1, which is 2.
Awesome. Okay, so we have 3 plus some nats of 2, and you were saying where you need to open a what?
A new local execution context.
Indeed. Let's do it. And in fact, I'm going to make, well, no, if I need to make them smaller, I will, but we'll go with this for now. Okay, so in this case, the active context is sumnats 2.
Yes.
What's the call site?
So the call site is going to be some naturals 3.
Indeed.
Or some
and what else do we need to do?
And so the next thing that we need to do is declare within the local memory. Oh, yeah. So we're also going to need to push a new function into the call stack, sumnats with the argument of 2.
Awesome. Okay, now in local memory, what happens?
Local memory, we are going to assign n equal to 2.
And where do we go from here?
And then we're going to check the conditional statement if. So is if n, which is 2, less than or equal to 0? It is not. So we're not going to do whatever that conditional statement says.
What are we going to do instead?
And so we're going to jump down to the else statement and say return n, which is 2, plus the evaluated result of some naturals where 2 is -1, which is 1.
And we're invoking a function here. So what do we have to do?
So on the call stack, we're going to add some nats with the argument of 1.
We're going to push some nats of 1 to the
Can I
call
say
stack.
pop again?
No, you said add, but just
Oh,
for
add. I thought it said pop again. I
precision.
was like, oh my God.
Yeah, no, you're doing good. You're doing good.
Thank you.
And I am going to make these a little bit smaller so that we can fit everything here. Okay, so we have some nats 1 on the call stack. What else do we need to do?
So we're going to open up another local execution context where some nats is 1. And the call site for that is going to be some nats of the argument 2.
Awesome.
And
You
within
did
the local and within the local memory, n is going to be equal to 1. And so we're going to enter the body of that function that says the conditional if n, which is 1, is less than or equal to 0, which it is not. Definitely not. So we're not going to regard whatever is within that conditional statement. So we're going to jump down to the else statement, which says return n, which is 1, plus the evaluated result of some naturals, which is n, which is 1, minus 1. So we're going to push some nats of 0 onto the call stack.
This is exciting. What does that mean? In fact, let me just shrink this a little bit first. And then, okay, so I pushed some nats 0 onto the call stack. What do I need to do?
And so we're going to open up another local execution context. And the active context for this is going to be some nats with an argument of 0.
And what about the call site?
The call site for this is going to be some nats with the argument of 1.
Okay, walk us through it.
All right, so we're going to enter the function body and say,
Before we do that, what do we need to do?
oh yeah, the memory. That's right. In local memory, n is going to be equal to 0. And so now we can enter the function body and we can check the conditional statement if n, which is 0, is less than or equal to 0, which it is.
Hooray! So what do we do?
So we can return 0 now.
Okay, so we're going to return 0. Where are we returning 0 to?
So we're going to return 0 to the call site where some nats with the argument of 1.
Indeed. So now some nat 0 will be equal to 0. And we've returned out of this active context some nats 0, right? So what does that mean for this active context and the call stack?
So that means the JavaScript is going to garbage collect that, or it is eligible for garbage collection.
It is indeed eligible for garbage collection. And what else do we need to do?
And we are going to pop off some nats with the argument of 0.
Indeed, we are going to pop it off the call stack. All right. And now which stack frame are we in? Where is the thread of execution right now?
So now the toe is going into the sumnats with the argument of 1.
Indeed. Indeed. And how do you know that's where it is?
Because we returned 0 to that function where sumnats was with the argument of 1. Is that correct?
That is correct. That is where we return 0. Even more simply, it's the stack frame that's at the top of the call stack. And so our thread is going to be in that frame. But you are correct here. So we have the evaluator result of sumnats 0, which is 0. So what can we now do in this execution context?
So now, I guess to go back to the analogy that you said about tapping, people on the shoulder. So sumnats 1 was the second person in line, and sumnats 0 was that first person in line. So sumnats 0 is telling sumnats 1 that they're the last person in line. So they are going to return 1 plus 0 to sumnats 2.
So the return value of 1 is going to sumnats 2. And now I feel like I should not have made these so small. Can everyone read the text, or should I zoom back in? Okay, cool. Sumnats 1 evaluated to 1. So we're returning from this function definition. What does that mean for this this stack frame and the call stack?
So we're returning 1 to sumnats 2. So that means that the function sumnats 1 is eligible for garbage collection. And we're going to pop off sumnats 1 from the call stack.
Awesome work. And now where is our thread of execution? In which execution context?
So now the thread of execution has gone to the function where sumnats has the argument 2.
Indeed, we are here. And in this case, now we have the value of sumnats 1 to add to the number 2. And what does that equal?
So 2 plus the evaluated result of sumnats 1, which is 1, is equal to 3.
All right, so we have our return value. Where is this being returned?
And so that is going to return into the evaluated result of sumnats 3.
Into the evaluated result of sumnats 3?
Oh yeah, I guess not, because the evaluated result would be the return value from sumnats 2 into sumnats 3.
Yeah, so we are going to return this to the call site, which is in the execution context of sumnats 3, but it is the evaluated results of sumnats 2. So we will replace sumnats 2. We will evaluate this to be 3. And what can we do to this sumnats 2 active context?
And so sumnats 2 is eligible for garbage collection. And we're going to pop off sumnats 2 from the call stack.
Awesome, awesome. We're so close. What happens now?
And so now, finally, we're going to return 3 plus the evaluated result of sumnats 2, which is 3. And so we're going to return 6.
Indeed, and where are we returning 6?
We're going to return 6 to the global label output.
And why are we returning it here specifically?
Because that is where output was declared.
That is where output was declared in global. It's also where sumnats 3 was invoked, right? So output is the evaluated result of sumnats 3. So we will pair that, well, not pair it, but we will evaluate sumnats 3 and its value will be the value of output. what happens with our active context and our call stack?
So sumnats3 is going to get popped off of the call stack. And then output is going to have the value of 6 within global memory.
This is true. This is all true. There's one more thing that needs to happen.
Sumnats3 is eligible for garbage collection.
Fantastic. Awesome job, Nathan. You said you were nervous and we're going to try. You did great.
Thank you.
Really awesome communication here. All right, y'all. How do we feel about what we've just seen? We are invoking this sumnats. We're abbreviating it to sumnats, but sumnaturals function definition within the function definition of sumnaturals, right? This is what makes this recursion. Okay, we talked about the base case. Let's just call on some folks here. Let's see, Hudson, what was the base case in this scenario?
The base case was I think is it the whole line if n is less than or equal, less than or equal to 0, return 0.
Indeed. This is the smallest version of the problem. If we pass in 0 to sumnats, there are no numbers to sum between 0 and 0, right? This is the simplest part of the problem, the simplest version of the problem, the base case. And then, let's see, Eric, what is the recursive case here?
The recursive case is the else statement, where we return in plus some naturals, passing in -1.
Indeed, it is. And what is our initial value in this instance? We know the parameter is n. What is the value? Let's go with Gail.
Can you repeat that again?
Yeah, so we have an initial value for this instance. We know that the parameter is n, but what is the initial value? What is the numerical value that we're
3.
starting at? Yeah, the initial value that we evaluated in this case is 3. The parameter is n, but we could pass in 10. That's not a 10, Laura. We could pass in 10, we could pass in 20, pass in any number here as our initial value. This is called linear recursion. And we'll talk more about that after Connor's question. Connor, what's your question? I think you are muted.
There we go. Sorry, I was just curious. When we did the while loop, did we add the 0? Was the condition? What was the conditional there? I just wanted to see. Like, go back a slide.
Oh yeah, sure. Turns out to be a few slides.
Okay, cool. So if we did, yeah. So it was just in the chat. There was like in the recursion version, we did add the 0, but here, since it was greater than or equal to 1, we didn't add the 0. Cool. Thanks.
And y'all, this code, like this sumnaturals function definition, could be solved in a slightly different way. If we wanted to not add the 0, we could rewrite the code, rewrite our base case to return something slightly different, right? We could rewrite it to return 1 if n was equal to 1. I feel like I might have lost some folks right there. Anyone have questions about what I just said? Does that make sense? Thumbs on implementing this in a slightly different way.
Can you just repeat what you said one more time?
Yeah. So this is how we implemented this case of sumnaturals, but we could have chosen to say for our base case, if n equals 1, return 1, right? Or if n is specifically if n equals 1. Why is the way that it's written, that it's typed out, why is that a preferable way? In what case would if our base case was if n equals 1, return 1, what could we pass in as n and break our code? Anyone have any idea? What could we invoke some naturals with if our base case was if n equals 1 and have our function not work as expected? Yeah, Ryan.
0.
Yeah, if we passed in 0, then 0 does not equal 1. We would end up returning n plus some naturals of 0 minus 1. If we passed in anything that was less than 1, we would have a problem. Yeah. So in this case, if we wanted to use this as a base case, we would actually need 2 base cases, right? If n equals 1, return 1. But we would still need if n, oh, I missed the n. If n is less than or equal to 0, we would still need return 0, which is why in this case, this one covers both. Cool. We're going to look at an example in a little bit where we do have two base cases. Because that happens as well. Okay, other questions? Other thoughts? Okay, so this is called linear recursion. Okay. And when we talk about linear recursion, we're talking about, think about the line example, right? Once we get to the front of the line, that person has to kind of, the answer has to be what we'll call bubbled, and you'll hear this referred to when we're talking about recursion. The answer has to be bubbled back up. It has to go through each of these stack frames in order to get that final return value. Linear recursion, okay? I just want to make something super clear before we move on to the next piece. When we are pushing things to the call stack, let me erase some things here. What we're pushing is a stack frame, right? We're pushing a stack frame to the call stack. This is a stack frame. So technically, we're pushing stack frames to the call stack. Thumbs on this. We're humans and we need to be able to read what we're writing. So we're zooming in on them. But this is what's going to the call stack. Okay. And we also know that we open a stack frame, we open a local execution context when we invoke a function. And this is what gives us access to local memory, right? So when we are using linear recursion, we have this risk of stack overflow. And we also have a lot of stack frames being created here. So we're going to review the key idea of recursion, and then we're going to explore a method that doesn't require us to use so many stack frames. Okay, so the key idea of recursion, right? It's the question is how is this task self-similar? We see that in this case, the problem is self-similar because if n is 1, we return 1. But if n is 2, we return 2 plus the evaluated result of subnaturals of 2 minus 1. So if we keep following this pattern, using this n minus 1 pattern, we can move towards our base case and then bubble that back up to the very last person standing in line. Let's look at the same problem with a slightly different approach and again, pin that stack overflow issue in your mind here. Take 15 seconds and I'm going to call on a couple people to tell me something that they noticed that is different about this solution than the one that we just looked at. So just take 10 to 15 seconds. I use those times to drink water. All right, Winnie, tell us, and I don't need you to be super specific, but just tell us one well, I do need you to be specific, but you don't have to be super technical. What is a difference that you see between here and the code that we looked at before?
Base case returns result instead of 0.
Yeah, look at that. The base case is going to return result instead of 0. Thank you, Winnie. Let's go over to who have I not talked to yet? Jeff. Jeff, what else is different about this this code?
Not sure.
No worries, no worries. How many parameters did the sumnaturals function definition take in our previous example?
Oh, it only took one.
Yeah,
But,
yeah.
this one is mutating's not the right word, but it's iterating over both the arguments.
Yeah, we'll focus on the simplest answer here, which is there are 2 arguments. There are 2 parameters instead of 1. And Irene, do you know what's going on with this second parameter? Like what is going on here? Do you have any idea what this result equals 0 is about?
I just know that there is significance to putting the initial value in the parameter, but I don't remember why.
Yeah, there is significance here. It has a special name. Does anyone know what the name is? What do we call this when we assign some initial value? I don't know if an initial value is going to be applicable all the time, but when we assign some value here, what is this called? This is called, y'all, oops, let me go to my pen. This is called a default parameter. And what this means is that if we invoke sumnaturals with only one argument, that argument is going to be paired with n. And the second parameter, result, will be 0. So in this case, sumnaturals 3, n is going to be equal to 3. And result, even though it's not included here in our list of arguments, is going to be equal to what, Nina?
0.
Indeed, yes, it's going to be equal to 0. This is our default. It's what we will default to if the argument is not included when the function definition, when the function is invoked. Okay, what else? What else is different? Anyone else see anything different here? Let's go over to Roger. Do you see any differences here between this and our previous function definition?
Yes, on a return at the else return naturals, we do have invoked a result plus n.
So in this case, if the default parameter was 0, then result would evaluate to 0 plus n, in this case, be 3, right? So then result would be 3. But there's something even more important that I want you all to notice here. In this case, we are returning a function definition. We're returning the evaluated result of sumnaturals. We are not returning, and I'm going to scroll back to the previous code. We are not returning the evaluated result of sumnaturals plus something else. JavaScript has nothing else to evaluate in this line except this function definition. And this is going to be key to what we call tail call recursion. So in some languages, not all languages, and in some browsers, not all browsers, we can optimize our recursion by using tail call recursion. And what makes this tail call recursion is that we are returning the invocation of a function alone. There is no other evaluation for JavaScript to do here.
So just to reiterate that tail call recursion is when you're actually like messing with a variable in the parameter definition. Is that what it is?
Not quite, not quite. It is because you could have, so recursion is used for many, many different use cases, right? You don't necessarily have to be messing with the argument in some way here. There are other use cases where you wouldn't be doing that. What makes a tail call recursion is that this is a function definition, or excuse me, not a function definition. Function invocation that is being returned, and that is it. There's no additional evaluation. It's not being added to anything. It's not being subtracted from anything. It is this and this alone that is
Got
being.
it. So simply just calling a function, like calling another, like itself, with nothing being nothing being operated on the function label or whatever, that is tail call recursion versus linear recursion. There's something being operated, like something's happening, an operation's happening to the function like label, like before it runs.
That the distinction is that there is some other evaluation.
Right. That's what I was trying to say. Yeah, I didn't communicate that well though.
No worries.
Okay,
this
cool.
Is a confusing topic, and that's why we're spending just a little more time on it. Also, we're returning it, right? Like that's the other key component here. This is what's being returned.
Right. Cool.
Okay, we have some other questions. Let's go to Nathan, and then Irene, and then Winnie.
So I guess my understanding of tail call is like the most simplest way, this is probably incorrect, but the way that I understand it is that at the end of the function body, you're calling that function again to return it. And so tail call, I just think of like the bottom of the function. Is that correct?
When you say the bottom of the function, do you mean like physically in the function definition?
Yes, that's correct. Like at the very bottom of the function body, like for tail call to happen, it has to be the like the very last thing at the bottom of the function.
Yeah, there can be no code beyond this, right? Like if there was some additional code here, console log a, then this would no longer be tail call recursion, because JavaScript would have to, once it evaluated this, it would have to then come back to this stack frame, and we'll look at this in the diagram in a moment, and then evaluate this. So it is not just the, well, in fact, y'all, the thread of execution would end when we hit return. So it would never get to this line if we went into this else block. But if we didn't go into this else block for whatever reason and we didn't return, if there's anything beyond this piece, whether it is within the line, like sum naturals n1 plus 12, my favorite number, that would also kill this being tail call recursion, right? Because there's something else to evaluate. If there was code afterwards and this wasn't being returned, then it would also not be tail call recursion.
Awesome. Thank you, Laura.
Yeah, good question. Good question. Yes, I didn't name it, but I think it's reasonable to assume that it's called tail call recursion because it's at the tail of the code of the function definition, right? I think we can safely make that assumption, but maybe there's another reason. I don't know if anyone wants to dive down the rabbit hole of where the name comes from. All right, Irene, what's up?
I wanted to further, because it helps me to have like a visual. So if we could go back to the diagram that you had of the linear recursion, and I wanted to just use that as a jumping point. With the linear recursion, the main thing with this is that because we're returning not just a function definition, but like one plus a function that needs to be invoked, it essentially has to return what we get at the very end of this recursion and return it back up one level until we get back to the global execution context. And whereas I think I want to know if with tail call recursion, it doesn't need to do that. So it can just get to the, what's it called? The base case. And it can just return our result there.
It can. Isn't that exciting? Yes. Look at how this is possible. We'll diagram it and we'll see why this is possible. But yes, that is correct. So instead of the call site, let me not erase things. But remember, we have to return to the call site where the function was invoked. So the call site here, sumnats1, it has to go back to where it was invoked. The call site for sumnats1 has to go back to where it was invoked. We have to bubble back up. Each person in line has to turn around and say, yeah, there's one person in front of me. Okay, there's two people in front of me. Okay, there's three. We have to go all the way back up through each stack frame. In tail call recursion, we do not have to do that. And we'll see how that's possible.
The last person could just immediately tell you what's happening, right?
Yeah, it would be like if you like,
it basically doesn't have to loop through every person or every context back to the global, whereas Tailcase can just go straight back to global once the recursion has reached its endpoint.
Yeah, let's start the diagram. I think this is going, for anyone who's feeling confused, I think this is going to help clear it up. It's also going to answer that, it's going to confirm your suspicion, Irene, which is, okay. I know when you had your hand up as well, was your question answered?
No, but this is a great question. Let's just go with this.
Okay, yeah, let's go with it. Let's go with it. Okay, so Irene, I'm going to have you start us off here. We have some code here on the left. I should have erased that. And I'm going to have you walk us through this code.
Okay. Well, first we're going to I can't remember the exact word, but put down the function sumNaturals and assign it to a function definition.
And where are we going to declare this function?
Inside global memory.
Yes. Declare is the word you're looking for.
Okay, thank you. My brain just blanked.
No worries.
Once we do that, we will be jumping to, actually, is there significance in the, what's it called? You just told us result equals 0, that parameter.
The default parameter?
Yeah, is
not yet. So y'all, I'm just going to interject for a moment. Parameters are just placeholders, right? So until we invoke the function, JavaScript doesn't care about these, right? It's only when it's invoked and we have an argument to pair with our parameters that JavaScript is going to start to look at these things. So good question. Even though there's a default parameter, we're still just going to wrap all of this up in our function definition and then move on to the next piece of code.
Okay, so in that case, we can jump to the constant declaration of output.
And where are we declaring that?
Also in the global memory.
Awesome.
And once that is declared, we would push sumNaturals with the argument of 3 into our call stack and enter the local execution context.
Indeed. So we're going to open up a local execution context. Let's add it here. I'm going to make it a little bit bigger. Apologies for the interruption. So we have pushed the stack frame sumnats3 onto the call stack. We have opened up a local execution context for sumnats3. What is the call site of this function?
It would be the global execution context.
Sound like you're guessing, but you are correct. It would be global. All right, and what's the very first thing that we do when we open up an execution context?
We would match up the arguments with the parameters.
Indeed. And what is our what are our parameters here?
Our parameters here are n, which is equal to 3 in this case. And we have our default value result, which is set to 0 because we do not have assignment at this point.
Indeed. So our parameter n is paired with our argument 3, and result is paired with our default value of 0. Our default parameter is 0. We haven't passed in a second argument here, so it will default to be 0. Awesome work. Okay. Whew, we're doing it. We're doing it. Okay, what happens now?
Okay, so now it's going to start running through the conditional, and we will compare n to within n if n is less than or equal to 0. And because it is not, we move on to
Let's write that down. So what is n in this case?
3.
And is 3 less than or equal to 0? No. Okay, great. No, keep on going. You're doing great.
Okay, so now we move on to the else statement where we would return the function sum naturals. And we would be returning sum naturals with the argument of 2 and 2. No,
First of all,
3.
make this a little bit bigger so we can actually see what's going on. You said 2, and where did you get 2 from?
Oh, I meant 3 for the.
Yes.
Yeah.
Okay, so the first argument here is 2 because we're doing n minus 1. N is 3. 3 minus 1 is 2. And the second argument is 3. Put on my laser pointer. Is 3 because we've passed in result plus n. Result is 0. And n is 3, and 0 plus 3 is 3. Is everyone on the same page where 2 and 3 have come from in this line of code? Awesome. Okay. All right. We are invoking a function, but we are also returning from this function definition. So what happens here, Irene?
So we are returning this function definition. I know there's 2 options. One I'm a bit more sure about. I think most likely it's going to open another local execution context under what's called sum naturals with 2 arguments 2 and 3. The alternative that I think is unlikely would be returning back to global memory, the global execution context, and assigning that function to output, which I don't think that's right. Because it would return it, right? Actually, I don't know. I'm feeling less and less confident by the moment.
You're doing great. And in fact, your hypothesis, your latter hypothesis there is true. So what we're saying is the evaluated result, need my pen. The evaluated result of sum nats 3, that return value is the invocation of sum nats 2, 3, right? Let's just write that here. The return value is sum nats 2, 3. And we're gonna do a little bit of math, just a little bit of math, kind of math, logic here. If the return value of sum nats 3 is sum nats with the arguments 2 and 3, then we can say that sum nats 3 is equal to sum, well, first I have to be able to write sum nats 2, 3. Do we all agree with this statement? Is anyone confused about this statement? Okay. Because of this, because there's no other evaluation that needs to happen in our return statement, because it's just evaluating another function, and because that function is the same function for which we have our active context already open, for languages that allow for this optimization, for this tail call recursion, instead of opening another local execution context, what we are allowed to do, I have to make more space, what we are allowed to do is update our parameters in the current execution context. Because again, we're in the same function definition. And there's no other math for us to do. We're not adding sum nats 2, 3 plus 12. Best number in the world. Okay, y'all. This means that we are going to Should have left more space for this. We are going to evaluate sumnats 2, 3. And so Irene, just walk us through this. What is the first thing we do when we enter, when we invoke a function?
We match our parameters with our arguments.
Mm-hmm.
So n here.
Go ahead.
N here is equal to 2, and our result is no longer the default. It is now 3.
It is now 3. And then
And
what?
So now that we have necessary variables, we can go, or arguments, we can go into the conditional and check if n is less than or equal to 0, which it is, again, not. And because of that,
Go on. Yep.
because of that, we are going to return sumnats n2 minus 1, which is 1, and 3 plus 2, which is 5.
Yeah, and y'all, we're saying 3 plus 2 because result plus n, result is currently 3, and n is currently 2. Okay, so we're returning a function definition, and we are at, where are we right now? We're in sumnats 2 of 3, and in this case, we're just returning a function definition, and we know and when I say we, I mean JavaScript interpreting this, that if sumnats 2 of 3, if the return value is sumnats 1 of 5, that means that sumnats 1 of 5 equals sumnats 2 of 3. And so we don't need to open up. Oh, I didn't mean to forget to write that in. We're going to pretend that was there the whole time. We don't need to open up another local execution context. We already have one open for sumnats, right? So instead, we are going to update our arguments and we're going to keep on going from here. Irene, you're doing great. We're gonna pause for a question, and then we're gonna have someone else take it from here. Thank you so much. I know you said you were nervous at the beginning of being called on. Fantastic job. Kelly, what's up?
Why don't we close the local execution and then go back into it?
I think you would have to talk to the people who implemented this to really know that. But the optimization that tail call recursion gives us is that we will only have to open this one stack frame for this scenario. And so one reason to do that is now we can avoid a stack overflow. It doesn't mean we're totally out of the woods. We can still cause some problems with our computer if we forget our base case, but we can avoid the max call stack exceeded.
Okay, thank you.
Yeah. Why would you want to close and open a new one?
Well, when you're returning the invocation of the function, wouldn't you be returning it back into the global execution context so that it will leave the local execution context?
That's a good question. And also a good kind of logic and reasoning about that. I guess it's possible that this is under the hood, that it is being popped off and then replaced with a new one. But I'm not sure exactly kind of the intricacies of how that works. What you do need to know, and the takeaway for this in particular, is that the power that this gives us is to avoid stacking frames on top of frames like we saw in our previous piece. But that's an interesting thread to pull on. I'd be interested to know what you find.
Okay. Thank you.
Yeah. Y'all are on it tonight. Winnie, what's up? Oh, you put your hand down. Is this your question from before?
Sort of. I think that answered it because I thought like return always means you go out of your execution context. So you're returning that value to your global, and then now you're going back into a new local. So technically you're not really adding on to your call stack, but you just keep replacing the call stack. I don't know, but yeah, I think that's the same type of question.
Yeah, and like I said, the logic that, like, thinking through that is very sound in that way. So I wouldn't be surprised if that is the case, which would also mean that we're facing a different problem. No longer a Stack Overflow, but an endless single stack being regenerated if we forget our base case or miswrite our base case in some way. Winnie, since I have you here, why don't you walk us through this from here? We are in SumNats 1 and 5. What's the first thing we're going to do?
So we pair the parameters with the arguments. So n is 1 and result is 5. And then we look at the conditions. Is n less than or equal to 0? No. So then we do, we return some naturals n minus 1. So 1 minus 1, 0. And then result plus n is 5 plus 1, 6.
Awesome. And we are returning. I've been forgetting to update the return value, but in this case, just like we saw before, the evaluated result of SumNats 1 of 5 is indeed SumNats 0 of 6. All right. And the more I think about this, the more I feel like y'all are correct in your logic, but I am interested to know if that is the case. Let us go through this very last piece here. Winnie, what happens now?
And then we do the same. So n, pair the parameters with the arguments, n equals 0, result equals 6. And then we look at the conditions. Is n less than or equal to 0? And is 0. So yes. So then we return the result.
And what is the result?
And the result is 6.
Result is 6. And where do we return this to?
We return that into the global memory under the label output.
Hooray! Amazing! We did it all with no more than 2 stack frames on our call stack, doing the same thing that we did before, right? This is the same problem solved in a slightly more optimized way. Not even slightly more optimized, I would say significantly more optimized. All right. How are we feeling about this, y'all? Questions? Thumbs? Any clarifying questions out there? All right, cool. We are just moving along, and this next one is a doozy. Okay. So there are different types of recursion. We've talked about a couple already, right? We talked about linear recursion. We talked about tail call recursion. And it was Nathan's question, I believe. Go to my highlighter. When we had linear recursion, the function call was not the last operation carried out. Remember, we had to add the invocation of some naturals to another number, to n, right? But in tail call recursion, a function call was the very last thing that we did. I don't know why my highlighter keeps disappearing, but we're just gonna go with it. The function invocation was the very last thing that we did. There was nothing else for us to do before we returned our return value. We are going to look at multiple or tree recursion. There's other types of recursion as well that we're not going to look at today. Perhaps y'all have come across problems where your outer function isn't recursive, it's an inner helper function that's recursive. Has anyone come across a problem like that yet? Those are real fun. Recursion in combinations, recursion for permutations, lots of different applications of recursion. But let's look at tree recursion. What happens when we call a function twice inside of itself? So first, before we even dive into the details here, is this tail call recursion? Thumbs up for yes, thumbs down for no. Is this tail call recursion? No, it is not. We'll see that when we look at the stack frame for this diagram. This is not tail call recursion, right? There is, once we evaluate one function definition, there is another function definition left to evaluate. So this is not tail call, no, excuse me, I'm saying function definition, function invocation. There's one function invocation, and once we evaluate this, there's another function invocation that we need to evaluate. This is not tail call recursion. This is multiple recursion, and it's multiple recursion because we are recursing, we're invoking a function's own function definition more than once inside of its own definition. So we're gonna see how many calls it would take to produce the fourth number of Fibonacci. Is anyone wondering what Fibonacci is? Y'all know? That's very impressive. I think the last time that I heard about Fibonacci before I spent time at Codesmith was, I don't know, many years before then, and it took me a moment to remember. So I'm just going to refresh your memories in case anyone is wondering and scared to say. So yes, Fibonacci is a sequence of numbers. It's actually a sequence of ratios that show up in nature in very interesting ways. And I'll let you explore that on your own time. But looking up the Fibonacci sequence in nature is an interesting Google rabbit hole. But basically, the Fibonacci sequence is going to start with 0 and 1 every time. And then every number after 0 and 1 is going to be the sum of the previous two numbers. So 0 plus 1 is 1, and 1 plus 1 is 2, and 1 plus 2 is 3, and so on. Oops. And 2 plus 3 is 5, and so on and so forth. So when I say n, I'm saying what number, what position in the Fibonacci sequence of numbers are we looking at, right? So the fourth number of the Fibonacci sequence would be what, Kelly?
3.
Yes, the fourth number is indeed 3. And what would be the seventh number? Hudson.
13.
It would be 13. Why do you say that?
Because it's the fifth and sixth numbers added together, 5 and 8.
Yes, 5 and 8 is 13. The numbers in the Fibonacci sequence, when starting with 0 and 1, will always be these numbers, right? The next number will always be the sum of the previous two numbers. So if we're looking for the 10th number, let me change to my pen. If we're looking for the 10th number, we know that the 10th number would be the 9th number plus the 8th number. All right. So this is Fibonacci. And in this case, we have two base cases. We spoke about this earlier, that we would come across this instance where we'd have two base cases. And the reason why we have two base cases is because, again, 0 and 1 are always going to be those first two numbers. So if we pass in 0, we're looking for the number, the 0th number in the Fibonacci sequence, then we are going to return 0. Switch back to my pointer here. And if we pass in 1 to the Fibonacci sequence, we're always going to return 1. 1 is always going to be 1. For the rest of them, we can programmatically figure out which what the Fibonacci number is based on this evaluation. So here's our base cases, plural, and here is our recursive case. Whatever we pass in as n, we know that I erased my 10 example, but if n is 10, then Fibonacci of 10 minus 1, Fibonacci of 9 plus Fibonacci of 8 will equal Fibonacci of 10. Luckily, we are not going to whiteboard Fibonacci of 10, y'all. That would be so wild and crazy. No, we don't have time for that. We'd be here probably till tomorrow. Okay, but we will do this piece here. We will figure out Fibonacci of 4. Okay, let's go. Let's get to the diagram. All right. Let's do it. Let's do it. This is going to be a heavy lift, but y'all got it. Let's see, Michael, you wanna walk us through this?
Let's go for it. So I don't know if you want to document this or if you want me to set it all up, but it looks like we've got the call stack. We're in the global execution context, and that's where our thread of execution is going to start. So it's going to start off by, we're going to be declaring a function with the label Fibonacci in the global memory and assigning it to the value of a function definition.
Awesome.
Perfect. And then we'll skip down to the next line in the global execution context, which is going to be declaring a constant with a value, or a constant with the label output that is assigned the value of the function Fibonacci with the argument 4.
All right.
So,
function, what do we need to do?
So that's gonna cause the thread of execution to go enter a new local execution context. Perfect, and that's going to push the Fibonacci function passing through the argument 4 onto the call stack.
All right, and let's just fill out this context here. What is the active context?
That's going to be the Fibonacci with 4 argument.
Oh my goodness. Oh, now is not the right time. Okay, 1 second, y'all.
I love that.
He's very into math. He's like, you're talking about Fibonacci? I'm here for it. I wish. No, he's just into interrupting at inconvenient times. Okay, the active context is fib4. Yes, what is the call site?
No, I love it. The call site is it was called from the global execution context.
Fantastic. Okay, and what is the first thing that we do?
We're going to be pairing the parameter with the argument in our local memory. So that's going to be n is assigned the value of 4.
Okay.
All right, then we're going to go through and it's going to, we're going to hit our base cases, which are if conditional statements. And our conditional statements are going to be if n is strictly, or so if the argument n is strictly equal to 0, then I guess, yeah, we'll look at that. It is not. So we don't have to do that conditional statement, and then we'll go to the next one, next if conditional statement, if which the condition is in this case 4 strictly equal to 1. It is not, so it will not enact that. Then we're now hitting our recursive case, and we're going to return the invocation of the Fibonacci function with the argument with the parameters n minus 1, and so it's going to be 4 minus 1, or argument. Yep, 3. Now I'm not certain. Are we going to go back up to the beginning of the Fibonacci? Oh, we're going to open a new execution context. That is the Fibonacci.
Okay, and you're right on, like, interpreting this how JavaScript would interpret it. It's not even going to, because JavaScript reads from left to right, it's not even going to go on to this next part of the line until it's evaluated this. But because we are humans and we need to remember things in a slightly different way, we are going to write out the second part of the line. So what would n-2 be here?
That would be 2.
Okay, great. Okay, so now, yes, we're going to open a new execution context. Which of these invocations are we going to open an execution context for?
The one on the left, because it goes from left to right. So it's going to be the new local execution context of the Fibonacci with the argument 2. I mean, excuse me, 3.
All right, and I am going to do some shrinking of these diagrams here so we can focus on the active one.
Perfect. Yep. Do you want me to tell you, or are you just, yeah, perfect.
And where else, what else do we need to do?
We're the call site was in the Fibonacci 4, Fibonacci with the argument 4.
And what do we need to do with our call stack?
It's now going to push a new local execution context of the Fibonacci with the argument 3.
Awesome.
Fibonacci function with the argument 3. Cool. So it'll then we'll pair the parameter with the argument. So that's going to make n equals to, or assign the value of 3. We've paired those, we now go to the conditional statements. The if statement does, sorry, I don't want to, I'm kind of like speeding through this but I can really be really technical if you want me to, but so it'll now go to the conditional statements, n equals 3. So if n is strictly equal to 0, which it is not, then we don't have to worry about it. Same with the next one. For the next conditional statement, 3 is 3 equal to 1. It is not, so you don't have to worry about it. So now we're going to hit the next line, which is going to be returning the into the invocation of the function Fibonacci with n-1. So it's going to be 3 minus 1, which equals 2. And then, yeah, also the Fibonacci with the value of 1.
And why is it 1?
Because n is equal to 3, and that it is n minus, so 3 minus 2, which equals 1.
Awesome. Okay, what happens now?
Just like we did before, but we're going to immediately enter a new execution context that is going to be the Fibonacci function with the argument of 2 passed in.
All right, so fib2. Let's take a, what's the call site? And then we'll take a quick pause.
Fib3.
Call site fib3. This is coming from this execution context.
Exactly.
And what do we do with our call stack?
We're going to push a new stack frame. I always forget it's 2 with the argument 2. I forget what it's called. I want to call it like frame stack and all these other things. Call frame. Anyway, so it's going to go through it again.
Before we move on, I just want to do a quick thumb check. Are folks following? Is anyone feeling like they got a question that they need to clarify where we are? We're all good? Okay. Yeah, Kevin.
Yeah, just a quick question. So like for JavaScript, would see Fibonacci n-1 and evaluate that first before it goes to Fibonacci n-2, like before invoking Fibonacci n-2?
Yes.
Okay.
Good clarifying question. Yeah. If JavaScript had invoked fib2 from over here, then we would need to have that stack on the call stack. A local execution context would need to be open. So because that's not happened, we know that JavaScript has not invoked that yet, but we will get there.
Okay, thank you.
That's a great clarifying question. Thanks, Kevin. Any other questions before we continue? Okay. All right, great. Michael, go ahead and continue here.
Okay, so now we're going to be pairing the parameters with the argument. So in the local memory of the fib2 context, so it's going to be n equals to 2. We're going to hit our conditional statements. If n, which is if 2 is strictly equal to 0, which it is not, so we don't have to worry. We'll get the next one. Is 2 strictly equal to 1? It is not, so we don't have to worry about it. then we're going to return the Fibonacci function with 2 minus 1, which equals 1 with the argument 1, plus the Fibonacci function with the argument of 0.
And where do you get 0 from?
Because it is n minus 2, n is 2, so that's 2 minus 2, which equals 0.
Okay, fantastic. So what happens in this case?
So now we're going to hit another local execution context.
And I'm going to shrink this one real quick. All right. I hope that is small enough. And add a new one here. Very good. And what is the active context for this?
It's going to be Fibonacci with the argument of 1.
All right, and the call site?
Fibonacci argument 2.
And what do we do with our call stack?
We're going to push I'm doing it again, a frame, a call frame, stack frame on top of there, which is going to be Fibonacci argument of 1.
Awesome. All right, walk us through it.
Perfect. We're going to be pairing the parameters. So it's going to be n is equal to 1. Now conditional statements. Is 1 strictly equal to 0? It is not. Is 1 strictly equal to 1? Oh my goodness, it is.
Hooray. Oh my gosh, what a moment. What do we do?
Oh my God. So we return 1. So that we now, we don't go down to the next line. We see 1. So that's going to mean that we exit this local execution context with it's going to turn into 1, essentially, the Fibonacci 1.
And where are we returning this to?
It is going to return to where it's going to look back up where Fib1 is in the scope just outside of it. So because it hits return, now we know that Fib1 is going to equal the integer 1.
Indeed. Okay, so.
And sorry, in this case, that would be the Fibonacci, that would be the local execution context, or the frame Fibonacci with the argument 2.
And I'm going to change the color just so that we can see this, since it is now so small. So that is now 1.
Yes.
Awesome. Okay. And what happens to this stack frame and local execution context?
Because we hit return, that means that the local execution context is eligible for garbage collection. So it's going to go away. It's going to get deleted out of the memory, and then the thread of execution and the call stack frame is going to be popped off of the call stack Fibonacci 1. Yep. So it's now going to enter the frame or the local execution context of Fibonacci 2 with the argument 2. And yeah, it knows that that is now 1. So it's now going to add, oh, wow. So now it's going to call the Fibonacci function with the argument 0.
You are doing awesome, Michael. This is our last diagram of the evening, y'all. So we're going to switch up. We're going to switch it up a little bit. Has anyone not had the opportunity to walk through a diagram yet, and is eager to give it a go? Hudson, happy to have you. Welcome to the spotlight. We are in fib of 0. I'm going to go ahead and push that to the call stack just to get you started inside of a local execution context. What's the first thing we're going to do?
So we're going to log n equals 0 to the local memory. And then we're going to go through the first if statement. Does n strictly equal 0? The answer is yes. So then we're going to log it to the call site fib2, return value of 0.
And where are we returning this to?
To fib2.
Indeed. So I'm just going to change my pen color again so that we can see this. fib0 has evaluated to the number 2. And what does that mean for our fib0 call, our fib0 stack frame, Hudson?
We pop it off the call stack.
Indeed. So we're popping this here off the call stack, and we are going to shrink. We are going to shrink our stack frame just for ease of seeing everything that's going on here. And what are we going to do with that local execution context?
It's eligible for garbage collection, so we just get rid of it.
It is. It's out to the curb, waiting for the garbage truck. All right, great. So where is the threat of execution now?
Now we're in fib2, and I think we just go straight to the return section of that.
Yes, and what is the return value?
It's 1 + 2, so 3.
It is 3. Oh my goodness. So exciting. What are we going to do with 3? Where is this being returned to?
Now we can put that 3 into fib3, I believe.
Indeed. So the local execution context of fib3. So this was fib2, and we are going to, sorry, I'm laughing. I can't even imagine what's happening behind me right now with this cat. Fib2 is going to evaluate to what, Hudson?
Is going to evaluate to, sorry, I got ahead of myself. It's to 3, yeah. And I was looking at fib1 of the next one.
No worries, no worries. All right, so we have returned a value from fib2. What do we need to do with fib2?
Now it's eligible for garbage collection, so we can get rid of it and pop it off the call stack.
Indeed, and it is already shrunk. Thank goodness. Pop it off the call stack. Here we go. And you were right to be thinking about fib1. What are we going to do with fib1?
Now we have to open a new execution context for fib1.
Indeed we do. The question at this stage of the evening is, am I going to be able to fit everything on the screen? Fib1, very good. We've opened it up. What's the call site for fib1?
The call stack, well, we push it.
Oh, yes, we do push it, yes. Good call. What's the call site? Where was this invoked?
Is to fib3.
It is fib3. All right, what happens first?
We log the n equals 1 to memory, to its local memory.
And just to be super specific, we're not logging n1, we're storing our parameter, or we are pairing our parameter with our argument. Our parameter is n, our argument is 1, and we're storing that in local memory.
So we're pairing our parameter of n with our argument of 1 and storing it in local memory. Okay, cool. And then we check our base case if n equals 0, which it does not. And then we go to does n equal 1, which it does. So we have then we return 1, so our return value is 1. And then we can put that return value into the local execution context of fib3.
So fib1 has evaluated to 1. Awesome. And what else are we going to do?
It's eligible for garbage collection, so we can get rid of it and pop it off the call stack.
We're going to shrink it first. Very JavaScript specific task. Just kidding. JavaScript is not shrinking things. That is just me, just the humans. I'm going to leave it. I will leave it here. Yes, and then it is staged for garbage collection, and you are correct. Popped off the call stack. Okay, anyone, and thank you, Hudson. Thank you, Hudson. Thank you, Michael. Anyone else want to jump in on this part of the diagram? Yeah, Nina. So we have just evaluated 3 and 1 inside of fib3. So what are we going to do with that expression?
So we are going to return 4 back to Fibonacci 4.
Amazing. We are returning 4 back to Fibonacci 4 associated with
With the Fibonacci, what's that? 3, right?
yeah, it's super small. Sorry, y'all.
Yeah. With Fibonacci 3.
Okay, so we've got the number 4 here. Awesome.
So Fibonacci 3 gets garbage collected and popped off the call stack.
Indeed. Indeed. Stage for garbage collection, right there at the curb.
So now we are going to invoke Fibonacci 2 and open a new local execution context and push it onto the call stack.
All right. Bear with me. I'll make this one a little bit smaller. I'll still write as big as I can. Since we've garbage collected all of these other ones, I'm just going to make them slightly smaller so that we can have some space for what we've got left here. Oh, no. All right. One moment. Bear with me, friends. All right, we're just gonna leave that over there. Very good, very good. Thank you for your patience, Nina. Let me just make this a little bit bigger again. So we are in the active context of fib2.
Fib2, and it gets the fib2 call stack frame. Stack frame gets pushed onto the call stack.
Yes. What is the call site for fib2?
Fib4.
All right. And what are we going to do?
So we are going to pair our arguments with our parameters. So n is 2. We're going to check our conditions if n strictly equals to 0, which is not true. We're going to go down to the next if statement, and if strictly equals to 1 is not true. And we are going to return Fibonacci 1 plus
why 1?
n minus 1, n is 2, so 2 minus 1 is 1.
Awesome.
Plus Fibonacci n, which is 2 minus 2, equals 0.
Hooray. Okay.
We are going to push Fibonacci 1 stack frame onto the call stack and open a new local execution context, Fibonacci 1.
And y'all, I just want to point something out here. We have already evaluated fib of 1, but we have already garbage collected what that evaluates to, right? We don't have access to that anymore. So indeed, JavaScript does need, based on the code that is written here, JavaScript does need to evaluate this again. So we've opened this up. There is a stack frame on the call stack. What's the call site of fib1 in this case?
Fib2.
All right.
So n gets the value of 1. We are going to check if n strictly equals 0, which is not true. If n strictly equals 1, so we meet this condition and we return 1 back to Fibonacci 2.
All right.
As the result of invoking Fibonacci 1.
Awesome work here. Fibonacci 1 has evaluated to the number 1. And what do we do with our active context of fib1?
So we are it's gonna get garbage collected and popped off the call stack.
Nice save there. Popped off the call stack. You are right. As I try and shrink this piece here. Very good. Staged for garbage collection, eligible for garbage collection, popped off the call stack. All right, what happens now?
We are going to invoke Fibonacci 0 and open a new local execution context and push it onto the call stack.
Indeed. How am I going to fit this on our slide? Let me just make this one a little bit smaller. Okay, I'm going to put it in the bottom right, and then we'll put it where it goes. Excuse me, the bottom left, and then we'll move it later. Okay, so, and also I think I accidentally erased that fib1 is 1. So this is fib0. You said we're going to push it to the call stack. You are correct. What is the call site of fib0?
Fib2.
Fib2. All right. Big moment. Walk us through it.
We are pairing n gets the value of 0. And we are going to meet our first if statement. Condition. 0 equals 0. So we are going to return 0 back to Fibonacci 2. As an output for Fibonacci 0.
Oh no. This is where my recovering perfectionism comes in. I don't like that this is differently sized, but that is okay. It is okay. We are all still following along. So we're turning 0 to the evaluated result of fib0. So what can we do now with the active context of fib0? This one
gets garbage collected.
Indeed.
And pop it off the call stack.
Okay, and then what?
And now we can return the sum of 1 and 0, which is 1, return back from Fibonacci 2 back to Fibonacci 4 under the evaluated result of invoking Fibonacci 2.
Oh my goodness, how exciting. What happens to the active context of Fibonacci 2?
Gets garbage collected and popped off the call stack.
I have been waiting for this moment. All right, what happens now in Fibonacci?
So now we have both results of invoking Fibonacci 3 and 2, and we get 5 and return it back to the global memory, under the label output.
Oh my goodness, we have it. And what happens to our active context?
It gets garbage collected and popped off the call stack.
Oh, thank goodness. Wow. All right. Round of applause for all of our participants in this massive diagram. Thank you all so much for the clear technical communication. I am going to move this over a little bit just so that we can talk just a moment about why this is called tree recursion. Oops, we're going to leave it. So we are invoking this function, Fibonacci, twice, right? Which is giving us this tree kind of structure. From Fibonacci 4, we invoke Fibonacci 3, we invoke Fibonacci 2. From Fibonacci 3, we invoke Fibonacci 2, we invoke Fibonacci 1. From Fibonacci 2, we invoke Fib 1 and Fib 0. Let me change my pen color so that this is more distinct. We'll go to purple. And this is taking on the shape of a tree, right? Do we see this shape of a tree? Yeah. I just wanna explore for a moment if I can move my Zoom piece. Oh, look, it's the top of my head. I just want to explore for a moment what this would mean if we wanted to calculate Fibonacci 5. So for Fib 4, we invoked Fib 3, which means we invoked Fib 2, which invoked Fib 1 and Fib 0. From Fib 3, we also invoked Fib 1. We go back up to, was that everything? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yes, from Fib 4, we had also invoked Fib 2, which invoked Fib 1 and Fib 0. If we wanted to calculate Fib 5, see if I can make this smaller. Oh. We would need to calculate Fib 4, which we already know is calculated with all these stack frames. And we would also need to calculate n-2. Why didn't that select? n-2, Fib 3. On this side. So we're just going up by one number, by increasing n by one number, we're adding an additional 1, 2, 3, 4, 5 stack frames to the stack. Tree recursion has this tree structure. Thumbs on tree recursion on this visual. Thumbs on why we are not diagramming Fib 10 tonight. Yeah, we'd be here a while. All right, y'all. Questions, thoughts on this piece? This is where we're gonna wrap up. We're gonna do a recap after this of recursion in general, and this is where we're gonna wrap up. So I want to give you all some time for questions. Yeah, Michelle.
Yeah, I just have a quick question about, so in the Fib 2 execution context, like then there's a Fib 0. I know that you put it, the evaluated result as 2. So I just wonder why it is 2.
Yes, it is not 2. I was wondering as we were calculating this, I'm like, I don't think Fib 4 is 5. Fib 4 is 3. Yeah, good.
Okay.
That was probably just a typo on my part. Someone probably said the call site was Fib 2, and I wrote 2. But in fact, well, apparently I can't erase just the 2. In fact, that should be what, Michelle?
0.
Indeed, which would ultimately mean that this does not evaluate to 4. It evaluates to, this does not evaluate to 3, it evaluates to 1, which means that this evaluates to 2. And we know that Fib 2 evaluates to 1. So in fact, Fib 4 is equal to 3. Great catch.
Yeah. Thank you.
Other questions? Other eagle eyes? Okay, y'all, let us recap. Let's recap recursion. It's an alternative to looping, right? We can solve these problems through iterative loops, through for loops, through while loops. Recursion is an alternative approach to that. What is recursion? It's when a function invokes itself within its own function definition. when a function calls itself. What happens in recursion is that a nested function level execution context is created, and we didn't draw a function we didn't draw those execution contexts within the execution context where they were invoked. That's why we had our call site that we were keeping track of. But ultimately, that's what's happening. We know that without a base case, we are going to encounter a stack overflow in linear recursion and other types of recursion. And we know that we can limit the number of stack frames that we need to compute our operation with tail call recursion. Now I'm not even reading the thing. Okay, let me read the thing. Nested function level execution context is created, and we add a new stack frame to the call stack. The thread of execution is going to enter the nested execution context, and all outer execution is paused, right? We are only ever working at the top of the call stack, the frame that's at the top of the call stack. And it's when we reach our base case that we are going to pass our return values to where the function was called, whether that was in global or whether it's bubbled back up like we saw in linear recursion. And in tree recursion, right? We're also bubbling back up in tree recursion as well. Anything else important here? We pass the return values to where the function was called all the way down to the initial call site that started the recursive process. All right, y'all enjoy the rest of your evening. Have a wonderful spring night.